and welcome to NPTEL MOOC on Fiber Optic Communication Systems and Techniques course. In the previous module we were discussing dispersion, and in this module we will continue to discuss dispersion. Okay. And we first consider some topic that we were just about to finish in the previous module, that of chirping introduced by the dispersion in the fiber as the pulse propagates through the optical fiber. Okay. And we have said that when the pulse is actually initially unchirped, that is, there is no phase variation across the pulse, that phase variation is actually induced, chirped, okay, because of dispersion, and this can be overcome by using what is called as pre-chirped pulses. Okay. The general expression for the electric field of a pre-chirped pulse, or at least the pulse envelope, will be, apart from some constant which I have taken to be equal to 1, is that you do not just have e power minus 1 by 2 t square by 2 t 0 square, but you actually have this parameter c, which is called as the chirp parameter. Of course, when you put c equal to 0, you obtain no chirp, that is when you actually call the pulses to be unchirped, and when c is greater than 0 or c is less than 0, you get two different types of chirping. I am not going to carry out the mathematical details. The mathematical details are essentially the same. You have to take the Fourier transform of this one and then multiply the Fourier transform with the transfer function of the pulse, and then you have to take the inverse Fourier transform. This is tedious, but I am not going to do that one for you, but the idea of, or the basic result of all this propagation equation solving or how doing all these operations is that the pulse width Tp continues to depend. Now, in addition to z, it will also depend on the chirp parameter c and beta 2. Of course, the dependence on z and beta 2 we already knew. So, the longer the propagation, the pulse would normally have become flattened and flattened, okay, or broader and broader, but now there is something very interesting that goes on. First, let us consider the case where beta 2 is greater than 0. I am going to assume that we are working with normal dispersion regime, okay, and then plot this Tp, okay, with respect to, or Tp by T0, let us say, which is kind of normalizing the pulse width with respect to the original pulse width as a function of z or z by Ld. So, many dispersion lengths have to be allowed, or the pulse has to propagate, so that these effects can become more pronounced. Okay. In the case when c is equal to 0, the pulse width increases linearly. So, this is the case when an initially unchirped pulse is launched, then its pulse width Tp continues to increase linearly with respect to the propagation distance. Okay. If c is positive, okay, then you will see that the slope actually increases much more rapidly. So, this is the case when c is greater than 0, okay, and the pulse width continues to increase. Of course, it is not really nice straight line, but please excuse that, this is actually straight line. Okay. So, these are straight lines, and how to get these straight lines is something that you are going to do it in the assignment or in the exercise. Now, let us make c negative. Okay. So, we have exhausted c equal to 0 and c greater than 0 cases. So, now we make c negative. What would you expect? It turns out that the pulse width actually decreases below that of the initial pulse width T0 for a certain distance. This distance we call this as z min. Okay. So, of course, normalized means, so you can write this as say zeta min, where zeta is by definition z by Ld. So, at a certain distance of the propagation, initial distance of the propagation, the pulse width actually reduces and then increases. This is a very interesting phenomena. Okay. What it means is that if you actually had a pulse which had a certain width here of some proportion to T0, the pulse width here actually is smaller. Okay. So, this T0 prime which I have written is actually smaller, and the pulse amplitude also would have increased, because in a lossless system the pulse width and the pulse height both have to be, the product of these two have to be constant, so that the total energy is always conserved. So, as the pulse broadens, the amplitude drops, but as the pulse compresses, the amplitude actually increases. So, what you are actually getting are higher peak power pulses. So, the pulse this one is higher in peak power, plus it has a narrower width or narrower pulse width compared to the initial pulse width. So, what we have actually accomplished is not so much as the pulse expansion, but so much as the pulse compression. And pulse compression is a very important topic in almost all ultra fast optics applications, where the goal is to go from say nanosecond pulses to femtosecond to attosecond pulse width. Okay. So, to obtain smaller and smaller pulse width, it is necessary to keep compressing the pulses. Of course, this is one of the techniques, but this is a very important technique. This is the technique that takes you from nanosecond to femtosecond. So, all you have to do is to either pre-chirp the pulse and then pass it through a fiber or any other material whose beta 2 is positive. Alternatively, the same conditions will hold when beta 2 is less than 0, but this time you change the sign of C. So, earlier you had C less than 0, correct. So, earlier you had beta 2 to be positive and you started seeing this pulse compression when C was less than 0, but now when beta 2 is negative, that is you are working with a material or you are working with a fiber whose dispersion regime is anomalous dispersion regime, then you just make C to be positive. So, essentially what you are looking for is the product of beta 2 and C, that is sign of the product of beta 2 and C, and if this sign turns out to be less than 0, that is both have opposite signs, then you will actually see pulse compression. Of course, you do not see pulse compression throughout, I mean you do not see a curve which would go like this, right, it would continue to compress out. What happens is that after a certain compression this one, then the pulse width actually starts to increase again. So, eventually you would have pulses that are broader, okay, at the output, but at least up to a distance of some zeta min, the pulse actually compresses, and this zeta min can be controlled by controlling the dispersion length LD via the parameter beta 2. So, you can actually engineer the value of beta 2 that you want, so that you can actually accomplish this pulse compression, and this pulse compression is a very important topic, as I told you, in pulse shaping at ultra fast optics. This pulse compression can also be put to some use for dispersion compensation. How? All I have to do is, or not all I have to, of course I have to do a lot of design ideas, but if I have a fiber, okay, whose beta 2 is positive, then a pulse that is launched into this fiber would actually have expanded the pulse width, right, or expanded the pulse. So, you would have had some chirping, plus the pulse width would have expanded when the pulse has propagated through the normal dispersion fiber. So, this is what would have happened when you have taken the information and then transmitted say from Delhi to Chennai. Okay. So, you have covered such a long distance. Now, at Chennai you do not want these pulses to be very broad, I mean they are of no use when the pulses have become so broad, because they are going to talk to the other pulses. Okay. So, you want to actually pull the pulses back into their original time slot, and you can do so by actually putting in a fiber whose beta 2 is opposite to that of the beta 2 of the transmission fiber. So, you have one leg where beta 2 is positive, you have another leg where beta 2 is negative. All that you have to ensure is that the total distance beta 2 times L 2 will be equal to beta 1 times L 1, where beta 1 is the rather beta 2 L 1 must be equal to beta 2 L 2, where L 1 and L 2 are the lengths of the first leg of transmission and the second leg of transmission. Okay. In fact, this is what is done in legacy systems, in many systems, where at the end of every span you actually put in a fiber whose beta 2 is actually negative signed as that of the forward or the span fiber. Okay. So, the span fiber usually is beta 2 with a negative value, then you put this beta 2 with a positive value, or if beta 2 is positive here you put a negative value. Effectively, the pulse which has started off with some T0 expanded out, and because it has now seen another an opposite sign of beta 2, it would actually start to compress. Okay. Of course, you have to adjust all the parameters correctly, so that the compression exactly cancels out the broadening induced by the forward fiber, and this technique is actually called as dispersion compensation in optical fiber communication systems. Okay. So, very important technique, something that we are going to see later in our course. Okay. One final topic of dispersion before we actually look at the causes of dispersion. This term, instead of using this group velocity dispersion and then using beta 2 to explain what is happening, okay, manufacturers of optical fibers use another term called as dispersion parameter, which is measured in picosecond per nanometer kilometer. Okay. What is the strange unit of picosecond per nanometer kilometer? What this unit simply tells you is that if your pulse actually has two extreme frequencies or extreme wavelengths, that is the Fourier transform of the pulse I am talking about, what is the group velocity of this one, what is the group velocity of this other end of the spectrum, right. The difference between these two over a length L or over a unit length L would actually correspond to the dispersion parameter. It would actually tell you what is the delay between the two edges of the pulse spectrum, okay, in arriving at a common point or arriving at the output of the fiber. Okay. So, how much delay is measured in picosecond, and what is the distance over which they have propagated is measured in kilometers, and what is the spectral width, that is lambda 2 minus lambda 1, which I will denote it as delta lambda, is what is measured in nanometers. So, in fiber optic communication systems and in most cases where you are dealing with light, it is quite common to use wavelength rather than frequency to describe the width. Okay. And this delta lambda is called as the spectral width. This spectral width of course is because of various reasons. You have your initial laser itself having this delta lambda, or you have your you are going to modulate the pulse, and therefore you kind of effectively expand or broaden the pulse width, that will have a certain delta lambda. So, all that delta lambda, what is the delay in arrival time between the two edges of the pulse bandwidth or the pulse spectrum is measured by this dispersion parameter d. Okay. And this dispersion parameter d is related because see d delta lambda L will tell you the total delay, correct. So, you have picosecond per nanometer kilometer multiplied by nanometer multiplied by kilometer. So, this will be the total delay, and in fact this delay is basically equal to tau g. Okay. And this tau g of course we also have seen from our earlier this one that it can be related to beta 2 omega square z, right, or beta 2 omega square. Okay. So, we have seen this one earlier as well, but without going into the details at this point, I do not want to give you too many mathematical details. This d can be rewritten in terms of, or this can be related to beta 2 by this expression. Okay. This involves converting delta omega to delta lambda, something that you do not need to worry about it at this point. And the main reason that I have introduced this dispersion coefficient or dispersion parameter d is because I want to show that d and beta 2 are related with an opposite sign. So, when beta 2 is greater than 0, you have what is called as normal dispersion parameter, when normal dispersion. So, in that case d will be less than 0, but when beta 2 is less than 0, you have what is called as anomalous dispersion, for which d is greater than 0. And if you look at this d, okay, you will see that the overall d actually goes something like this. It will go through 0 in the fiber at around 1300 nanometer, and at 1550 nanometer, okay, at 1550 nanometer the value of this dispersion d is roughly 17 picosecond per nanometer kilometer. Okay. So, what I have plotted is lambda on the x axis and d on the y axis. Of course, because after this 1300 nanometer, which is called as lambda ZDW, where ZDW is called as a 0 dispersion wavelength, the region here is actually anomalous, okay, whereas the region here is normal. Okay. And of course, this d with respect to lambda is not a straight line, d actually with respect to lambda is kind of a curve, and you sometimes introduce what is called as slope of the dispersion parameter, which I denote this as S lambda, given by del d by del lambda, and in fact this can be related to beta 3. Beta 3 is basically the third order dispersion, which is derivative of beta with respect to omega, the third derivative with respect to omega. Okay. So, these are some of the important parameters regarding dispersion. When you look at the data sheet of an optical fiber, you will see all these terms being used. But now the big question is, what is causing this dispersion? I mean, we have seen how to model dispersion, we have seen the effect of dispersion. So, if you actually send in two pulses, then both pulses essentially broaden out and then kind of overlap. So, this is what you would get at the output, while this is what you have sent at the input. So, you can't really distinguish one pulse with another pulse, and if you actually send it through an eye diagram, you will see that the eye diagram would be completely closed. So, you do not really see the system out there because of what is called as inter-symbol interference. So, this interfering of one pulse with respect to other pulse because of the broadening is called as inter-symbol interference, and that is the major effect of dispersion in communication systems. Of course, dispersion has other effects such as chirping or pulse compression, pulse expansion. There are other uses of dispersion as well, especially when you combine it with nonlinearity. Those are all some different applications that we do not want to go, but we want to understand where this dispersion is coming from. Okay. To do so, I will do a little bit of a hand waving. Okay. These results are actually taken from a paper which I mentioned to you earlier, okay, by Glog. I think it was 1971, I do not really remember, I will give you the details later on. But what he showed in this paper is that for the linearly polarized modes that we are talking about, you can define a propagation constant, a normalized propagation constant as beta over k0 minus n2 divided by delta times n2. Okay, where delta is being redefined by this paper as n1 minus n2 by n2, okay, where n1 is the core refractive index, maximum core refractive index, n2 is the cladding refractive index, and the difference delta is n1 minus n2 normalized with respect to n2, and this b is the effective index related parameter, and v of course you already know is the normalized parameter. So, normalized frequency parameter or normalized frequency 2 pi by lambda a times n1 square minus n2 square. Okay. What he did was to actually rewrite this beta, which is the propagation constant, in terms of the refractive indexes of the fiber itself. So, you are now looking at an expression where beta can be written as k0 n2 times 1 plus b times delta, where b is the propagation constant of the mode that is propagating, and of course, you know from our earlier discussions of LP modes that there are many modes, and therefore, you have to be careful as to which mode is propagating. Okay. So, of course, if you look at that famous diagram that we have actually plotted for B versus V, you will see that this is for the case of 0 1 mode, and then you have a group of modes or which are essentially 1 1, and then you have kind of 2 1 0 2 modes which are very close to each other. Of course, this cutoff is occurring at 2.405, and this cutoff is occurring just about 4. Okay. So, do not worry about the actual numbers, but if you look at these different modes that we have, right, and if you were to zoom out in any one of those modes. So, let us say I zoom in on this one, okay, what I actually see is this curve, okay, and I would actually have sent in a pulse whose spectrum would be this way, right. It has some V min, it has some V max, okay, and because of this V min and V max there is a difference. So, you will now have B max and B min, and you see that this is not a linear relationship. What you actually see the relationship here, which say B0 with this as V0 as the center, is not an exact replica of this one. So, it is not a linear relationship, and because of this being non-linear in relation, what happens is that the propagation constants actually depend on what lambda that you are transmitting or on what the pulse width of that you are transmitting, and most importantly these parameters are now further functions of V, and the derivatives of these are what is going to give you the dispersion in the fiber. Okay. But we do not normally do it in that way, we actually go back to the delay tau g that is that we express, and this tau g we write it in terms of the simple d beta by d omega that we already know, which is of course beta 1 parameter. You can adjust this expression d beta by d omega by differentiating beta with respect to k naught and then differentiating k naught with respect to omega, where k naught of course is given by omega by c, where c is the phase velocity, and you are simply writing this dk0 on both sides, so that the entire expression is still the same. Okay. And but of course, because k0 is in this way, so dk0 by d omega will be 1 by c. So, this is actually equal to 1 by c d beta by dk0. Okay. And now what I am going to do is to readjust this equation, because I want to bring in the normalized parameter or the normalized frequency parameter. So, I am going to consider this as d beta by dv times dv by dk naught, and I know that v is given by k0 square root of n1 square minus n2 square, a k0 square root of n1 square minus n2 square, and I can rewrite that one. So, dv by dk naught will actually be equal to v by k naught. Okay, I can substitute that into this expression, and since I also have written beta as k0 n2 1 plus b delta, I can find out what is d beta by dv, and therefore write tau g as, please verify this expression, okay, v by k naught d by dv k0 n2 plus d by dv b delta k0 n2. I have just expanded this beta into this one, or expanded that out and then differentiated with respect to v, and dv by dk naught is basically v by k naught. So, I have just considered that one, 1 by c comes in with 1 by c. Okay. Now, when I actually carry out these derivatives, what I get is that I get 3 terms. Okay. I will tell you the importance of these 3 terms very shortly. So, what you actually see here is this one, right. So, I know what is n2 by c, that is simply the phase delay kind of a thing, right. But then I also have dn2 by dv. What does that mean? V is the frequency, and with respect to n2, when you are looking at the derivative of n2 with respect to frequency, this would mean that the material property that you are considering of the fiber, the cladding material n2 itself is dependent on the frequency. So, n2 is not the same for all frequencies, but n2 changes. Of course, it changes for frequency, means it is also different for different modes. Okay. So, this change of n2 with respect to frequency is not really in my control, okay, because this is the parameter property itself. So, these 2 parameters, the first and the second term, are actually what is called as material dispersion, because they relate how beta or the refractive index n2 is changing with respect to the frequency as a consequence of the material property. So, if you want to change this dn2 by dv, or you want to shape that one, you have to actually experiment with different materials, because each material has its own dispersion, which is has its own material dispersion, and therefore, this term is something that comes because of the material itself, and that there is normally not a lot of control once the material has been selected. But the term that is there on this right hand side is what is called as the modal dispersion. Okay. Modal dispersion in turn can be broken up into inter and intra, which means that if I am going to consider only a single mode fiber, the propagation constant B will be different and it will be nonlinearly related, but it will still be with the same single mode, right. So, this is called as intramodal dispersion. But if I have launched my optical pulse such that the spectrum goes over like this, therefore, it is propagating in some mode as 0 1, some portion is also propagating, or the next mode is also excited, then because the propagation constants are different for the 0 1 mode and 1 1 mode, the part of the light that is excited or exciting into the 1 1 mode will travel with a different velocity as the part of the light that is excited as 0 1 mode, and this difference is called as intermodal dispersion. Intermodal dispersion is quite common, and in fact is one of the major problems in the multimode fibers, whereas intramodal dispersion sometimes is called as simply chromatic dispersion, is an important parameter in SMF. Okay. But our formalism would simply want you to know what is beta 2, and therefore, does not really depend on whether you have applied it for a single mode fiber or you have applied it for a multimode fiber. But it is interesting to see that this modal dispersion, okay, comes because of 2 effects, as I have told you. Okay. So, is there anything that we can say more about the modal dispersion? Yes, you can show, and I will give you the notes for this one in the class by actually carrying out the derivative, that you can write this as N2 delta by C and then d by dV times BV, okay, where B is the normalized propagation constant, as you already know, and further expression for d by dV times BV is something that is not easily obtainable, but there have been approximations that people have used. For example, one approximation is 1 minus kappa square by gamma square. I do hope you remember what kappa and gamma are, times 1 minus 2 kappa nu square divided by kappa nu minus 1 kappa nu plus 1. Please note that nu minus 1 and nu plus 1 are the orders of the modes that we are talking about. So, this derivative itself can be approximated this way, okay. And if you actually plot this tau modal as Gloag has plotted in his paper, and you look at that one with respect to V, you will see that for 0 1 mode you will actually see something like this, okay. The normalized modal will be 1, most of the modes actually asymptotically reach this 1, but if you go to different modes, for example 1 1 mode would look something like this, and then you have a 2 1 mode which goes something like this, then you have a 0 2 mode which goes something like this. So, this is for 0 1, this is for 1 1, this is for 2 1, this is for 0 2 and so on. So, these modes actually have farther away, of course, from the cutoff, the modal dispersion or the modal delay can be approximated as N2 delta by C, and they actually have a max modal delay at different values of V number. Okay. So, far away from the cutoff you actually have this approximation for all of them, okay. And this intermodal delay that I talked about essentially asks you to find out what is the maximum excited mode, so for which you have a max value of V and then you have a min value of V, okay. So, what is the delay in arrival between the max and the min values, and you can actually use another equation for that, which will give you approximately this condition. Of course, this condition is not okay for nu equal to 0 and nu equal to 1, but for other modes this is reasonably okay. And when you look at this expression and calculate what would be the difference between say nu 2, that is the second nu equal to 2 and say some nu max, okay, you will see that this intermodal delay, okay, this is intermodal delay can be approximately written as N2 delta by C 1 minus 2 nu max. So, when you start exciting larger and larger number of modes, then you will also see that intermodal delay depends on this one, okay. And this further can be approximated as delta by C 1 minus pi by V, V being the parameter that you already know. So, this is an expression for intermodal dispersion, but for a single mode operation there is no intermodal delay because there is only a single mode, but in that case you are dealing with intramodal dispersion, and that intramodal dispersion also can be obtained with some approximations which we are not going to discuss now. So, the net effect is that in dispersion in optical fibers comes because of materials and because of the waveguide itself. All these terms that intermodal, intermodal, depending on V, depending on B actually came from the waveguide properties. Therefore, the total dispersion is a sum of material and waveguide dispersion. We will have to say a little bit more on dispersion in the next module, and then consider what is called as polarization mode dispersion. Thank you very much.